Hey guys, in this video I'm going to go over all of these topics. This video is not really meant to be entertaining in any way, but more kind of informational. I hope you read my disclaimer, and if you go on my site, you can see for my design there's a bill of materials, there's some design calculations, hookup, schematic, even a DigiKey card, some pictures, and again more disclaimers. And in this video, I'll go over all of these topics kind of at length. Earth grounding strategy is a big one that I'm talking about quite a bit just because I think it's important to understand it and not just do something just because someone else does it, but understanding it and you know, getting a second opinion and doing what you think is right. So I hope you enjoy this video. And if you have any questions, just go visit my site and you can email me with any comments, questions, or concerns. Hey guys, I've had a lot of people building their own amplifiers lately, so and you know, a lot of questions and things like that, so I thought I'd make a quick video just focusing only on my electrostatic amplifier design just to make it easier. And so this video will be very helpful if you're trying to build this amplifier. So basically here's an example of the amplifier that I've built, and I would recommend this type of chassis. It's got a lot of space that you can work with. It has ventilation on the top, it's metal, and you know, it's just a nice enclosed box. I think you might be able to still get this on eBay. If not, you know, there are various other options available. Notice here that I'll have two plugs here. This is a DIN plug and this is the Stax plug. I used to use the DIN, and then I just added this recently, and now I'm trying to commonize towards the Stax ProVise plug because it's just compatible with Stax amplifiers and then also my amplifier. So I'm just trying to commonize to this, but this also poses its own challenges. So one of the available plugs on Headamp is this plug. You can find it on eBay. Just Google, you know, Stax plug basically, and it's a pretty nice plug. But unfortunately, I use the Moon Audio Stax connector, and they're both, obviously both of these are not made by Stax. They're off, you know, third-party stuff, and these don't really mate too well. You'll notice that when you plug it in, it will kind of get stuck like this, and it's pretty difficult to push it in all the way. So I don't really like that because I think it creates kind of a safety hazard, because now you have this exposed plug. And one way I got around that, this one's not too bad, but one way I got around it is I went and took a drill and I made these holes wider so that there's more room for them to wiggle. And I think it's really just the tolerance of how close they are together that's causing it, and not necessarily the wideness of it, but it's the spacing. The pin spacing is not exactly you know, 100% accurate, but you know, this will work really well with a normal Stax plug, but it doesn't really work that well with the Moon Audio Stax plug. And the same thing, the Moon Audio Stax plug works really well with the actual, you know, OEM Stax amplifier. It's just that when you get these two together, they don't fit perfectly. Anyway, there's two things you can do to get around that. One is buy this if you can still get it, because I think they're out of stock right now, and then very carefully take a drill and widen these holes. You can remove these pins. These are actually, you can actually find these pins on eBay. They're vacuum tube socket pins. You might be able to find them by searching for something like that, but you can get them on AliExpress or eBay. They're actually not that hard to find, and once you do find them, they're not hard to purchase. And what you can do is unscrew these and then drill a hole and then screw them back in, but you have to be very careful not to drill all the way through, because then the base of this pin is no longer going to have a place to sit. So if you drill all the way through, when you put this pin in, it'll just fall right through. So I've actually broken one by trying to do that, so I don't know, you just have to be very careful. The other option is to make your own. And here I've just taken a piece of plastic and I've CNC'd this myself, and I can share the DXF file or STP file to drill your own, and that's what I've done here. I've just made my own, and it works out nicely. It's recessed in there so that, you know, it's kind of a little bit nice to have it recessed so that nothing's exposed, and yeah, it fits pretty well. So yeah, that's kind of all I need to know about that. And you know, I might be able to CNC this for you and work something out, but basically I have two pieces. I have this, and then I have a PCB on the back here that when this, so that it, and they're glued together so that when this pin actually goes through here, it has somewhere to sit. And I'll show you what I mean by that here in a second. So you can see what I'm talking about. There's like another PCB. So basically this one has the wider holes and this one has a smaller hole so that has somewhere to sit. Here's the connector I was making. There's just a piece of plastic here that I CNC'd, drill the holes, and then this is a piece of FR4 that has smaller holes in it so that these little pins can fit in there, and then there's little screws that attach to it, so you can see what it looks like. Another consideration with the DIN is that, you know, it could be misinterpreted as a plug that's used for something else and not a electrostatic amplifier. So someone could plug something else in here and potentially damage it or cause some sort of hazard that, you know, it's good to avoid. So, you know, the common stacks is probably a good way to go there as well. Another thing is I've created some warning labels and things. You know, they're nice to have a label for where the grounding screw is. Okay, and one of the first mistakes people often make is when they put this PCB together, which is kind of the easy, you know, it's like the easy part, right? Putting all the components on and soldering them. They will forget that you need to leave these standing off of the board by, you know, like an inch or half an inch or so that it doesn't transfer heat to the PCB, right? And it has enough airflow so that the high wattage resistors can dissipate that heat into the air rather than getting claustrophobic and transferring the heat to the PCB and self-heating. So you really need to help to keep those standoff, because a lot of people want to make it really tight and make it look nice, and that's not really good for these resistors. You want them to kind of stand off like that. The other thing is, you know, obviously this layout's pretty tight, so you want to make sure that you're not shorting things out, and, you know, there's resistors and things that are a little bit too close for comfort for me. So for me it's okay, but, you know, I wouldn't like be comfortable if, you know, someone else did something like that. So I had to use these wide heat sinks because this was kind of added later, and so the tall heat sink was going to interfere with this, so I ended up going to this wide heat sink, which works, but the spacing is pretty tight. So what I would recommend is using these taller heat sinks where the spacing is a little bit better, and then just getting the spacing of the chassis more accurate such that you're able to use this. One of the things that I'm going to talk about as well is this grounding on the secondary. Okay, so here's the transformer. It's the 272BX. This is kind of what it looks like, right? So you have 120 volt primary. The data sheet was messed up. It said black and black, but it should be white and black. And you have 120 volts primary. You have 600 volts output, 5 volts AC output, and a 6.3 volts AC output. And the 600 volt output is center tapped. So you have essentially, you know, 0 600 or 0 300 300, depending on how you want to look at it. And so these really, I only use these two windings, and this third winding can be used. You can connect it to a series resistor and LED, and you can use it as an indicator LED if you want to. so here's my design basically, and you can see here's your large voltages, right? So you have plus 386 volts here and minus 386 volts here, which is probably what you're going to measure. You have your 600 volt center tap input in, which is the same thing as here. That's your ground minus plus, and those are your 3 wires that go there. And this is all in the hookup diagram on my site too, so that's helpful as well. And then the 6.3 volts goes here. It goes into a voltage doubler, so you can get an 18 volts and a 9 volts. Really, because of the diode drop and the variation of this, it's really more like 16 volts and 6 volts, or 16 volts and 8 volts. Yeah. And then also you have the way each channel works is you have your input going into an input buffer, and this is a non-inverting configuration, so it has a gain of about 3.4. Then it goes into a non-inverting input op amp and an inverting input op amp. So this signal is up like this, and then this signal is inverted, and then the FETs really amplify that signal. So then you get the big output like this, and then your headphones are connected across here. Basically each headphone is connected here and across here. The bias, the high voltage bias, is generated with this another doubler that uses one of the legs of the secondary transformer, and I kind of just remove this one because I used to have a divider here so that you could step down that voltage, but now I get rid of this, and just that bias goes through here. You can use a 20 or 30 meg resistor here to help slow down that current, limit that current, and it seems to work pretty well. So for the grounding strategy, it's pretty interesting. Basically, I've drawn up this diagram here. You can see that this is the metal chassis, this is the PCB, here's a transformer, here's some of the wiring, not all of it. Here's the audio input, and that goes to a potentiometer that's used to control the volume, and then from the potentiometer it goes into the PCB, which I've identified as left, right, and ground. There's kind of 2 grounds that I'm going to talk about. The first ground is the earth ground. That's the 3rd pin, or the 3rd prong on the AC plug. Okay, basically here, this is your ground, right? And then your earth ground. Then the other 2 are line and neutral, right? That's 120 volts AC. That's very dangerous. And what you do with that earth ground is often it's used to tie to the metal chassis, right? And that's to add safety, because if your line ever pops out for some reason and touches the chassis, now your chassis is live, it's 120 volts. If you touch it, you'll get a shock, and if you touch that and some ground reference, it'll go through your heart, and it could be very dangerous. So what you do is you tie the chassis to earth ground. That way, if line ever touches the chassis, it'll blow the fuse, or if it doesn't blow the fuse, for whatever reason, it at least will have some ground reference where it would rather go through the chassis, through the earth ground, and not through your body, right? So that's the whole point of grounding it here. You use a nut that's very difficult to remove, and there are certain UL standards and things that define a lot of this stuff that you can look up and do it to those standards if you so choose. The next step is the understanding the signal ground. So the question is, what do I do with this signal ground, right? Because you have your line and neutral coming in, then you have a transformer, and then you have your power on the secondary winding of the transformer. So your primary and secondary are magnetically coupled, so they're isolated. They're only really connected through magnetism, right? And so the question is, what do I do with this signal ground, which is the ground reference of your PCB? Okay, that's a very interesting question because, so one interesting thing is that most often what happens is, or this is what was happening to me, was that I was grounding the secondary with the auxiliary plug, right? And so what's interesting about the auxiliary plug is this outside metal sheath is often tied to your signal ground pin. So you can take an ohm meter and ohm between here and here, and you'll find that these two are connected. So what that does is when you tie this to the chassis like that, and now it's connected to the chassis, your secondary ground is now also tied to the chassis, and therefore it's tied to earth ground. Okay, I did not see anything wrong with that necessarily, but that's what was happening, and it's important to know that that's. I used to leave this like that and just have this connected to the chassis, and I was fine with that because now my signal ground, which I've identified here, which is the same thing as the the middle pin on this secondary winding. Anyway, the signal ground of the PCB was now tied to earth. Okay, and one of the byproducts of that is that if you have this connected to earth, so this signal ground is connected to earth, and then you plug in your source, let's say your audio source is from your computer is earth grounded. So what happens is this signal ground on your computer is probably tied to earth ground. Okay, and so what happens is when your signal comes in, it goes into the it goes into the amplifier, it comes out, and it should go back to the source, right? All current should always go back to the source. Well, if this is tied to earth, to the chassis, the current could go in to the PCB, and then it could go, instead of going back to the source here, it could travel through the chassis, through earth, through your house wiring, earth ground connection, and back to the computer, and then back to the source that way. And that creates this large loop where there's a little bit of current going through this large loop, and that large loop can induce it, and it could create voltages, and eventually what you will get is just basically hum. You'll have this 60 hertz hum that you can hear if this is connected to the computer. So then the question is, okay, well then I should just remove that ground, right? I should isolate this somehow, use a piece of PCB or some sort of thing so that this is not really connected to the chassis. Well, I didn't like doing that because now my secondary is fully isolated. And also what I noticed when that happens, you hear a buzz, right? So something about this floating induces a buzz either through parasitic capacitances or RF and things that it's picking up. So it really does like to have some sort of earth ground reference, right? So this secondary thing, if it's floating, it's not floating relative to earth, creates buzz. So it's good to have that some sort of earth ground reference. So what I do is I do isolate this by using a piece of FR4, but at the same time I'll intentionally have another chassis ground where instead of doing a direct short to ground, I'll use a little 10 ohm resistor, and that 10 ohm resistor now helps reduce that buzz, right? So 10 ohms is small enough where I have no longer have buzz, but it's large enough that there's no ground loop, because now the current from your computer source or whatever comes in and it goes back to the source. There's too much resistance to the chassis for it to want to go this way. Now, a tiny amount will, but it's going to be a lot less than if it was a direct short, right? So that's one way of doing that. Now, the second question is, from a safety perspective, what happens for whatever fluke reason, let's say this thing gets struck by lightning or something, right? And there is a short between the primary winding, 120 volts, again, this is very dangerous, to the secondary, right? So let's say there's some sort of a short that happens here. This insulation breaks down and it creates this arc, and now it's shorted. So now that's kind of a hazardous condition, because now your secondary is no longer really floating. It's now tied to 120 volts, right? So that's now live. So you would think that since your signal ground is now earth grounded, you'll have current that flows from here to here through signal ground and to your chassis, now to earth ground, right? And so then that's going to blow the fuse. Well, maybe not, because maybe or maybe not, right? Because this is a 600 milliamp fuse. This could fuse open, before this does. Or let's say someone defeats this fuse and just puts a short in here for some reason. They did something really stupid. Well, now you have a 20 amp breaker, right? So this 10 ohm resistor has to handle 20 amps, and it's not going to. It's going to toast. It's going to fuse open and just be toast, right? So what you can do is, and this is what I'm doing, is you put a pair of anti-parallel diodes like that, right? So it's basically two diodes back to back in parallel with the 10 ohm resistor, right? And this is tied to the chassis, and this is tied to your signal ground, right? And so what that does is it basically the resistor is now there for buzzing, but the diodes are there for kind of a safety thing, right? So if this ever happens, now your diodes turn on, enough current goes through to either blow the fuse or trip the breaker. But you have to make sure your diodes are sized for like a 25 amp pulse current, right? So that's what I'm doing, because assuming a 20 amp breaker, if I can get a 25 amp pulse current, either this fuse or the breaker is going to trip before these diodes go and blow up, right? So that's kind of the strategy there, and I'll show a video of how it's all hooked up. But I just use that ground of this. That's where I tap the signal ground and put the anti-parallel diodes and tie that to the chassis. But like, I guess you could do it here, but it's a little congested. I worry about that shorting or doing something bad there. There's other places where you can do it on the board, but this is where I chose to do it just because it's most out of the way of everything else, and seemed like the safest way to do it. Yeah. So anyway, I hope that helps just to understand what my grounding strategy, right? So basically you have an earth ground tied to the chassis, so your chassis is earth grounded, and then you also have a secondary grounding, but it uses a different strategy to accomplish a couple of things: buzzing, hum, and safety, right? There's no perfect solution. I haven't really tested this. I haven't gone and done a forced a failure here or something like that to see if it would work, but in theory I think it should work. But again, if you want to get a second opinion, you can. I've talked to a couple people, and I've noticed a couple people do this sort of strategy. So that's what I'm doing. You don't have to do it. It's up to you. This is your DIY project, but thought I would try and get that information out there. Okay, so you can easily see I unscrewed this, so you can see kind of what's going on. So you have, this is your plug here. You have line, neutral, and this one is going to be your ground. And there's this amp case is nice because it has a fuse in here, a fuse holder in here already. So that's my 600 milliamp slow blow fuse that goes in there. And then you can see that it's wired, after the fuse, it's wired to the switch. And then when the switch is on, you have 120 volts applied across here. You can see that I've secured this. This is a ground for me, and I've secured that directly to the chassis with a lock nut that can't be easily removed, and you don't want anything else connected to this. This is just the ground for the chassis here. And then also notice here, this is I used the signal ground from the 3.5 millimeter jack, right? So the signal ground for that jack is here, and then that's where I tied the anti-parallel diodes and the 10 ohm resistor to the chassis ground. So this is the secondary signal ground and how it's connected to the chassis and therefore earth, right? Now, there's other places where that ground exists, for example here, right? So this is also the signal ground, that middle pin, but I'm not wiring anything to that. I chose to do it from here. And obviously without this PCB, or without the isolation of this sheath from the chassis, then this would be pointless because it would be directly shorted with the sheath to the chassis. So that signal goes in, it goes to the potentiometer, and then from the potentiometer it goes here. So the potentiometer just divides down the signal. And I just have a cheap potentiometer, and you can get like, you know, $30 potentiometers that have, you know, are much better matched and probably have better properties. But what I try and do is just keep it at maximal, the potentiometer at max volume, because then that just kind of just bypasses it really. It just sends a signal directly through, and then it's just as good as a, you know, it's just uber expensive one, and then you can just control the volume with your source. So, you know, if you really cared that much about that kind of stuff, then you still don't have to spend a ton of money. You can get around it, but if you want to spend a ton of money, that's good too. For the chassis, here's a bunch of different tools that I used. Not gonna go over them, but just different types of tools that kind of come in handy. This was CNC'd because I did try and drill my own holes, and you can see they're a little bit offset, and I didn't like the way it looked because it was like not perfect. So I ended up this is for a different amp, but I ended up not liking this because the screws weren't aligned perfectly. So I ended up using a CNC to cut these, and it turned out pretty well. And then the other thing is, because the potentiometer, the neck of that threading is not that wide, you have to kind of when you use these amps, the thickness is too thick, so there's not enough width to get that threading through. So I had to like thin this out, and I use this to do that, and it's not fun actually. This is probably the most out of when building this amp, this is probably the part that I like the least, because this is not really meant for aluminum, it's meant for wood, and you have to be careful. Basically drill a pilot hole and then you know, route this out so that you can fit the potentiometer in here. And a CNC would probably work better, honestly, but I just started using the CNC and learning how to do that. But before I had a CNC, I'd just use one of these tools, and it's not fun, but that's the main challenging part of this. And maybe someone can come up with a better way of doing that. Okay, so real quick on dimensions for the PCBs. For the blue one, it's 147 by 120 millimeters, and then for the red one, it's 147 by 125 millimeters, and they're both exactly the same, except this one's 5 millimeters wider. For the chassis, it's 21 centimeters by 9 centimeters height by 22 centimeters deep, and I wouldn't really go any smaller than this. For the transformer dimensions, which are pretty critical as far as making sure it fits inside the chassis, along with the printed circuit board and all the added components, just Google the 272BX, and you will have to obviously look this up anyways so you can understand how it's hooked up, and you'll find the data sheet will provide the dimensions here, and then you can look at the diagram to show how it's hooked up, as well as the dimensions from the data sheet. Hey guys, so in one of my previous videos you've seen me with a screwdriver and adjusting this resistor here until I measure a correct voltage at each of these right plus, right minus, left plus, and left minus. And I wanted to spend a couple minutes just talking about what's actually happening and what you're actually doing when you're doing that. There is you're adjusting these resistors so that you are properly biasing this end MOSFET, right?
So you have your gate to source resistance. You have a 310 ohm resistor here, which is a very small resistor. That's just there to kind of protect it from shorting if you actually pull this all the way to 0. And then this, they have this 10K here. And really you want to measure when everything's off and you're just populating it, and you adjust these resistors. You want to measure from minus HT to the gates, each of the gates. You want to measure about 2.8K, right? And so that is, that tends to be a good starting point to make sure your final goal is that your output for each leg of the driver is 0 volts relative to ground, right? So the whole point is you have a plus high tension, or I call it HT, 386 volts, and you have a minus high tension, 386 volts. And as you know, the electrostatics are very high voltage, so you want the drive to sit at 0 volts, and then it'd be able to swing all the way up to 300 and all the way down to minus 300, right? And so to be able to get that full swing, you want this to be close to 0 volts relative to ground as possible. That way you have a full swing with minimum opportunity for distortion or clipping at the higher levels, right? To achieve that, you need the right amount of current to be drawn here so that you get enough voltage drop across this 50K to make sure this is 0. How do you make sure you get enough current bias for this FET? Is that you bias the gate to source voltage just at the right amount so that it allows enough current through to hit that, get this at 0, right? So you want your DC current, meaning your direct current, to be enough such that your output is 0, and then that way when your audio signal comes in, it adjusts that AC current to be in line with the audio, and then that 0 volts can swing up and down to give you your audio output. Okay, and so when you just build this up, really what you're doing is you're measuring between the gate and the HT for each of these, and you want it to be about 2.8K, and you're using your screwdriver to do that. Everything's unpowered when you do that, so it's low risk. You know, you don't have anything connected yet, and you get 2.8K across here. Okay, now when you finally do build it up, now you're measuring the voltage, not the resistance anymore, the voltage between A ground, which is here, and the output. So between A ground and R plus, A ground and R minus, A ground and L plus, and A ground and L minus, you want it to be close to 0. It might be 4 volts, it might be 40 volts, it might be minus 20 volts, but you're now measuring this voltage, and you're adjusting this resistor to give you that right 0 volts again. So maybe this is 2.8K, maybe it's 2.9K, maybe it's 2.7K, but whatever it is, it needs to give you an output close to 0. If it's 4 or 5 or even 10 volts, it's probably fine, but you want it to be as close to 0 as possible. Now, when you do that though, be extremely careful. You know, basically when you power everything off, what I do is I will measure the voltage while it's powered, and then I will disconnect, and then if I need to adjust it, I'll disconnect the power, I'll turn the resistor one way, I'll power it back on, I'll measure the voltage again, and if it's too high, then I turn it back off, I turn the resistor the other way, turn it back on, measure it again, if it's too low, turn it the other way, and just keep going like that. But I only turn the resistor when it's powered off. I don't try and measure the voltage while turning the resistor and having, you know, both hands here, and you're kind of clumsy and you could slip, and very dangerous. So just be very careful when you do that part of adjusting that resistor and measuring that voltage. So I just want people to be aware that, you know, just take your time, don't do anything stupid, and just be careful when you take those measurements, because it doesn't take that long. So just be careful and be cognizant of how you're turning on and off the power, and even unplugging things to make sure that it's not energized. Again, you still have capacitors that are very large, that are very energized, that can still give you a nasty shock if you touch something that that's energized. So just be careful at that part, and you should be good.
Okay guys, I hope you found the video helpful to build your own amplifier. Again, if you don't feel comfortable building it, don't build it. There are other options available. You can find some cheaper used Stax amplifiers. Here's the SMR1 MK2. It's one of my favorites. It has an encoder that has where you can turn the left and right knob separately to change the volumes of each channel differently if there's a channel imbalance, or and then there's also the this is the SRM 252S, and but this smaller amp is not as powerful as these two. You can probably find these two on eBay for a pretty reasonable price. Probably not as low as you can build this on your own, but I don't want to give out prices because they're probably always changing anyway. So, but yeah, if you search for the SRM 252S or the SRM 1 MK2, and I'm sure there's a whole bunch of others, you should be able to maybe find some good cheap amps out there. And if anyone knows any more amps that they can purchase at a good price, leave a message in the comments. And thanks for watching.